In week 8, we're continuing this same idea of the confidence intervals that we started in week 7. We're just going to be talking about a different kind of distribution. We're talking about the student T distribution. Now, I know since we are students, we might think that it's named after us, but it's actually named after someone who discovered it, created it. His pen name was Student. So that's why it's called the student's T distribution. Why it's needed is because usually we don't know the population standard deviation. The problems we worked with a z-score, it took into account that we knew the population standard deviation. We just didn't know the population mean. Well, in reality, we often don't know the population standard deviation, and we still want to calculate a confidence interval. So we're going to look at a couple of different ways to do that, and it is with this T distribution. So the T distribution is going to be used just like the Z distribution, but it is going to normalize what we're talking about to where we are actually going to take into account the sample size and some other things. So the formula you see in front of you is to solve for our T, which when we were doing it last week, we solved for Z. It wasn't the same formula, but we solved to get our Z value, and we used that in the equations. Remember when we were talking about the 68% percentile or the 95th percentile, we had a set z-score. 1.96 is one of them, right? That we use quite a bit. So this time we're actually going to solve for a different number, and it's going to be our student's T score, usually just called a T-score. But right here we can see the components of it, right? We have X bar, that is the mean of our sample, minus mu, which is the mean of the population. Here S is our sample size of our sample, obviously. I'm sorry, that's not the sample size. N is the sample size, and S is the standard deviation of the sample. So we don't need the standard deviation of the entire population like we do with the z-score. So let's see how we use this. Here's the properties. You can read through those. Usually students aren't real interested in what the properties are, but they are there, and I think we've covered pretty much the parts that we need to know about it. You can always refer to that. So I'm going to move my face down a little bit. So when we use a t-score, we're going to talk about t is the random variable. If we have a sample size n equals 20 items, then we calculate the degrees of freedom. It is just n minus 1. It would be 19. We would write the distribution then as t, large T, equals T19, 19 degrees of freedom. That was looked up on a chart. I think we'll use the calculator mostly this term, but we would look down actually the degrees of freedom, meaning the sample size is super important with talking about how far away things are from that mean. If we have a large sample size, then we can go ahead and probably use the z-score. But we have smaller sample sizes, we need to use that t-score if we don't know the population standard deviation. The error bound for the population mean is written this way. And what that means is t to the standard deviation divided by 2 is a t-score with area to the right that is equal to the error, that alpha error, divided by 2. Use the degrees of freedom of n minus 1, and S is the sample size. This is really just lots of definitions right here. The format for the confidence interval then is our X bar, that's our mean of our sample. We can easily get that, right? Sample size, add them up, divide by the number in the sample. So X bar minus that error or plus that error, right? We're adding it or subtracting it, so we're getting this confidence interval, that idea. So we have some information for the calculator to start to calculate confidence interval directly, stats, tests, and press down to number 8. It's the T interval if your calculator is a little bit differently configured, and push 8. You can push 8 instead of going down to the interval. Here's the type of problem that we would use this. Here we have a project working to understand the scope of industrial pollution, and we have 20 blood samples from newborn infants. And here's the results of how many chemicals were found in each infant's cord blood. kind of gross, isn't it? Kind of a lot of chemicals. So use this data to construct a 90% confidence interval for the mean number of targeted industrial chemicals to be found in infants' blood. Now, we don't know anything about our population. We just have this sample information. So first, we're going to calculate our mean. And we do that by adding it up and dividing it by how many. So I'm just going to go back to this chart for a minute. We see that we have some very large numbers. Our smallest numbers, 70, 80, 90. So it makes sense that when we calculate this, our mean is 127.45. We can also calculate our standard deviation right on the calculator there. If we put all those numbers into the list, we can calculate the standard deviation of this sample of 25.96. There are 20 infants in the sample, so N is 20. Our degrees of freedom is 19. So we have all these basic numbers to work with. We're asked to calculate a 90% confidence interval. Now, t-scores are different than z-scores. We aren't going to have one pat number that every time is going to work for 90% because this changes with our degrees of freedom, how big our sample size is. So we will have to calculate this every time. So our CL is 0.90. And so our error there is 1 minus that, right? It's the other part, the part that isn't. So that is 0.10. So when we do this calculation of our alpha over our 2, we divide 1.1 by 2 and we get 0.05. Therefore, our t is to 0.05. Okay, we just put that from our calculation right into that. So that's how we write it. By definition, the area to the right of this number is 0.05. I think I always have to draw a picture, right? So if I'm looking at 90%, okay, here's my mean. This is 90%. I'm looking at 90% in here. That means I have 10% to split between here and here, which means 5% is going to be in the tail, 5% is going to be over here in the head, and if I write that as a decimal, it is 0.05. Okay, that's where those numbers come from, and that's what it's talking about. The area to the right of this is 0.05, and the area to the left of it is 0.95. If I go all the way here, it's 90% plus that little bit of 5. Okay, just to maybe help you with the visual, use a table or a calculator or computer to find that our t-score of 0.05 is 1.729. Now I'm going to enter that in here, and this time, notice I put that number here. That's where I get this number here, okay? But I still am going to work in this sample size. So it's going to change, and it's about 10.038. So that's my error, and I will subtract it from my mean and add it from my mean, and I get this interval. So if I start here at 117 something and some change, go up here to 137 and some change, 90% of I'm 90% certain that the mean of my population will be found in those numbers. So with 90% confidence, our mean number of these targeted chemicals is going to be between those two numbers. Hopefully working through that helps, and you can refer back to this if you need to for some of the homework problems. On the calculator, here's some information for that. We're going to do the t interval, and then you want to make sure that you enter your data first off. Enter the data as a list. Then you can access that list and the confidence level and calculate, and it will give you that confidence interval. Is that easier? Yes, of course it is. But hopefully you'll understand what it means by seeing the other way first. Here we have a population proportion, which is just a little bit different. During an election year, we see articles in the newspaper that state confidence intervals in terms of proportions or percentages. So, for example, a poll for a candidate running for president might show he has 40% of the vote within 3 percentage points, if the sample is large enough. Often election polls are calculated within 95% confidence. So how do we do that? What are we talking about? The procedure to find these confidence intervals. the sample size, and the error bound, and the confidence level for the proportion. It's pretty close to what we've been doing. We've got a little bit different formula though for it. So here we have, this is our proportion. Okay. How do you know if you're dealing with a proportion problem? First, it's going to be a binomial distribution. There is no mention of a mean or average. Okay. It's yes or no. That's what we're talking about. Either they're for a candidate or they're against a candidate, or they're not for a candidate, whatever way you define it. You just have two choices. And you don't have the mean. To form a proportion, you're going to take x, which is a random variable for the number of successes, divided by n, the number of trials or the sample size, and we get our p prime. That is proportion. Sometimes a random variable is denoted as p with a hat on it. I had a book once that actually denoted it as the Greek letter pi, which made no sense to me because pi should always be 3.14, right? So there's different ways of denoting this, but this is the proportion, which makes sense. If we're dividing something by the number, then that is going to give us a proportion. When n is large and p is not close to 0 or 1, we can use a normal distribution. It's a much easier formula to approximate the binomial. If we divide the random variable, the mean, and the standard deviation by n, we get a normal distribution with the proportions p. And this is more familiar to us when we use this, when we have that large sample size. In algebra, we just are simplifying. We're going to do some cancellations here, and we have p prime follows a normal distribution for proportions. X divided by n equals p prime, which can be written as n with these two, the interval, so it has 2 points. So to do a confidence interval, we have to find that error that we're going to add to the p prime or subtract from the p prime. So the way we're going to do that is this formula down here. Our z, again, alpha divided by 2. Think back to our normal curve, and the part that is not included is going to be our alpha. And we're going to be adding this little component here. This is the probability that it does happen. Q is the probability that it does not happen. So if we are 30% going to happen, then we are 70% that it is not going to happen. These have to add up to 1. And we divide by n and take the square root of it. That gives us our error that we are going to be adding and subtracting here. Thought it was going to change. So this formula is similar. The error bound formula for standard deviation, it's a similar one. Standard deviation is just going to be this p times q divided by n. Remember, p is the probability it's going to happen, q is the probability it's not going to happen. In the error bound formula, we use p prime and q prime as the standard deviation instead of p and q. So you're just talking about the proportions rather than the percentages. Let's see if we have an example coming up. Success and failure. That's what our confidence interval is. Used only if the number of successes n times p, a large number, and the number of failures in q are both greater than 5. So in very small sample sizes, we cannot use this. This is kind of a shortcut way to do it. So notice that that is a good rule. We want to have both the possibility it could happen and the possibility it couldn't happen. Both of those numbers, those percentages times my sample size, are going to need to be greater than 5. So let's look at an example finally and try to make some sense of what I've been babbling on about. For a class project, a political science student at a large university wants to estimate the percent of students who are registered voters. He surveys 500 students, finds that 300 are registered, so we have 200 that are not. Compute a 90% confidence interval for the true percent of students who are registered voters and interpret the confidence interval. So the first step, we're going to go through a step-by-step solution, and then we are going to do it on the TI. So you can tell me which one you think is best. So here's our information, right? We have the voters total, and if I want to go back here, if you're talking about the registered voters and the total number of students is 500. So we can get this proportion. How many students are registered? Well, 0.6. Okay, so we know that when I have my P and my Q, we're talking about 0.6 for the P, 0.4 for the Q. They have to add up to be 1. Confidence level is 0.9, and then we do our alpha, which is going to be 0.1 divided by 2. Again, those two tails of our normal curve. So then we get this number for our z-score. And using the calculator, and we're going to do the inverse norm of 0.95. Where do we get 0.95? Well, that is everything but that one tail, right? We want to talk about the greater than. So we're going to put it in this way. The area to the right of the 0.5 is the 0.95. Okay, 0.05. Then we can calculate using a computer or standard normal probability table. Here we have our error by taking this number and our P prime, Q prime divided by N. Here it is in numbers, okay? I have our 60%, our 40% divided by 500. Take the square root of that, multiply it by the z-score that we got, and we get 0.036. So I'm going to add that and subtract it from my probability, the percent of voters, right, because that's what I'm talking about, plus or minus, and I get this confidence interval. Okay. So we estimate, and you can read that, the true percentage of registered voters is going to be between those two numbers, and there's some alternate wording in there. 90% of the confidence intervals constructed this way contain the true value for the portion that are registered. So let's see what the calculator can do for us. This one, we still use the calculator a little bit, but to get the 1z number, but let's see what else the calculator can do. So we're going to go to stats and tests, and we're going to go to 1 prob z int and push enter. Then down arrow and enter 300 to x, down arrow to n and do 500. That's our data, right? Confidence level of 0.9, calculate, and we get the answer. So the calculator is very useful on this one. I think you will agree. And here's some down here just for you to try. I think that it's good to know how to use your calculator because you will get precise and quicker results. Nobody needs to spend hours on any stats problem anymore. However, I think knowing what that normal curve looks like, what you're really trying to find, and why those little numbers are there is rather important. That was funny, it just changed while I was waving my hands. Okay, so calculating the sample size. Sometimes we want to know what the required sample size would be. We want to make sure we are sampling enough to cover our margin of error. So you can use the error-bound formula to calculate just using it backwards to calculate the sample size that we need. So when we're going to solve this, I just usually use E for this, just the error. It's a lot easier to write as you're doing calculations, and you solve for N, meaning the sample size. So I want to get everything else on the other side. Remember algebra, and then you are going to square it to get rid of the square root sign, and we have N equals this rather strange, not that complex because you understand what all those pieces mean, I hope, but you get this equation for the sample size. So this is just one of those examples here. A mobile phone company wants to determine the current percentage of customers over a certain age who use text messaging. So how many customers age 50 should the company survey in order to be 90% confident? So this is the kind of problem that would use that formula here. So we would just figure out these same numbers that we would if we were going to try to find the confidence interval, but we're kind of working backwards to find the N. So we can just plug them all in and solve for N. And that way you can find out that you're using a correct sample size. A lot of information in this one. Good luck. Let me know what I can do to help.